This is Pre-Calculus, Section 3.2, Day 2 Notes. Hello, math friends. Today we are still talking about dividing polynomials, but right now what we're going to do is take what we learned in our previous section about division of polynomials and synthetic division, and we're going to use that to introduce some interesting theorems that will help us to find solutions to polynomials. So in example 1, it says that we should use synthetic division to find the remainder of 2x squared plus 6x minus 5 divided by x minus 2. X minus 2 is a linear factor. Remember that the c value is always the solution or the opposite of the factor. So if the factor is x minus 2, then the value of c that we're going to be putting outside the bar is going to be positive 2. So here's my division bar with my positive 2 c value. My coefficients are 2, 6, and negative 5. I'm going to drop my 2 down and multiply. 2 times 2 is 4. I'm going to write it and I'm going to add. 6 plus 4 is 10. 2 times 10 is 20. I'm going to write it and I'm going to add. Negative 5 plus 20 is 15. So this is my remainder, this is my constant, and this is my x term. So my solution is 2x plus 10 with a remainder of 15 over x minus 2. In example 2, they want us to find p of 2 for that same polynomial, 2x squared plus 6x minus 5. Well, we know that p of 2 means we're just supposed to substitute 2 into the equation where we see the x. So p of 2 is going to be equal to 2 times 2 squared plus 6 times 2 minus 5. And then if we follow PEMDAS and we do that math, we have to square 2 first, which is 4, and multiply by 2, which gives us 8. 6 times 2 is 12, minus 5. 8 plus 12 is 20, and 20 minus 5 is 15. Interesting. Okay? So I want to point something out to you. When we divided that polynomial p of x by x minus 2, we had a remainder of 15. When we substituted in 2 for x, the value that we got was 15. So what we notice is that dividing 2x squared plus 6x minus 5 by x minus 2 gives the same result as substituting x equals 2 into the equation. Imagine that. This result leads us to the remainder theorem. If a polynomial p of x is divided by a factor, a linear factor, x minus c, then the remainder will be p of c. So let's prove this one more time. Here we have a new polynomial and we have a new c value. Let's use synthetic division and the remainder theorem to evaluate p of c. So if we were going to use synthetic division, they're telling us that c equals negative 3, so we're going to keep the sign, which really means we're dividing by the factor x plus 3 if the c value is negative 3. Now be careful here. I see that I'm missing an x term, so I'm going to have to put a 0x in right here. Always got to hold the spot of any missing terms. So my coefficients are going to be 1, 2, 0, and 7. I'm going to drop down the 1. Negative 3 times 1 is negative 3. 2 plus negative 3 is negative 1. Negative 3 times negative 1 is 3. 0 plus 3 is 3. Negative 3 times 3 is negative 9. 7 plus negative 9 is negative 2. This is my remainder, my constant, my x, and my x squared. And just to verify, the degree of my solution is 1 less than the degree of the polynomial that I started with. So I know that I did this correctly. But what I'm interested in right now is my remainder, which is negative 2. So what this remainder theorem is telling us is that right now, if I go ahead and I do p of negative 3, my answer should be negative 2. Let's see what happens. P of negative 3 is going to be equal to negative 3 cubed plus 2 times negative 3 plus 7. Negative 3 cubed is going to be negative 27. 2 times negative 3 is negative 6. And then we have a positive 7. Negative 27 minus 6 more is going to be negative 33. Oops, I have an error here. My apologies. This is 2 times negative 3 squared. Let's backtrack. Sorry, negative 27. Negative 3 squared is 9 times 2 is positive 18 right here. Oops, oops. And then plus 7. Okay, now we're going to add these together. Negative 27 plus 18 is negative 9, and negative 9 plus 7 gives me negative 2. So as you can see, I got the same result. Zeros of a polynomial correspond to factors of a polynomial. This is something that we know because one of our methods for solving a polynomial is to factor it and then set each factor equal to 0. And the relationship between the factors and solutions is that the solutions are always opposite of the factor. So example number 4 is asking us, is x plus 3 a factor of p of x equals x squared plus 7x plus 12? And they want us to show 2 ways to determine the answer. Okay, so the first way is I am going to factor the polynomial and find out if it is a factor or not. So if I'm going to factor p of x equals x squared plus 7x plus 12, then I'm looking for a pair of numbers that multiplies to make 12 and adds to make 7. And I know that that pair of numbers is going to be 3 and 4. So my factors are x plus 3 times x plus 4. And so as you can see right here, yes, x plus 3 is a factor of the polynomial. Okay. Now the second way that I'm going to show this is by using synthetic division. So in essence, I'm going to divide the polynomial by x plus 3. But again, if I'm dividing by x plus 3, that means that my c value that I'm going to put outside the bar is going to be negative 3. So I'm going to put my negative 3 right here. My coefficients are 1, 7, and 12. I drop down the 1. Negative 3 times 1 is negative 3. I add and I get 4. Negative 3 times 4 is negative 12. I add and I get 0. Okay, this is very significant. So let's talk about what this means. A remainder of 0 means c equals negative 3 is a solution of the polynomial, and x minus 3 is the factor it came from. Okay. So a remainder of 0 means 2 things are true. It means that x plus 3 is a factor of p of x, and it means that x equals negative 3 is a 0 of p of x. That's pretty powerful information for us right now. And that information leads us to the factor theorem. And the factor theorem says that the factor x minus c is a factor of p of x if and only if the remainder is 0. Oops. Or p of c equals 0. Show that the given value of c is a 0 of p of x and find all of the other zeros of p of x. Okay, so we're going to start with synthetic division. I look at my polynomial. I've got x cubed, x squared, x and constant, so I'm not missing any terms. I'm going to put my C value outside the bar and my coefficients across the top. 1, -3, -4, and +12. I'm going to drop down my 1. -2 times 1 is -2. I add and get -5. -2 times -5 is +10. I add and get 6. -2 times 6 is -12. I add and I get 0. Okay, so what this just proved is, yes, x equals -2 is a solution, which was part of my job, right? I had to prove that the value of C was a 0. And yes, x equals -2 is a 0 of the polynomial or is a solution. But now I have this new polynomial to factor and solve. Essentially, we've divided out that factor of x plus 2, and what we have left is the polynomial that's remaining, which 0 is the remainder, 6 is the constant, -5 is the x term, and 1 is the x squared. So this polynomial is x squared minus 5x plus 6. Well, that polynomial is also factorable. Two numbers that multiply to make a +6 and add to make a -5 are going to be x minus 3 and x minus 2, which tells us that the two remaining zeros are +3 and +2. So now I've done everything that I've been asked to do. I showed that -2 was a 0 of the polynomial p of x, and then I found all of the other zeros or solutions, because remember, zeros is another word for solutions. Finally, the last part here is kind of the opposite of what we just did. So if you want to find a polynomial that has specified zeros, like in example 6, they're telling us that our polynomial has a degree of 3, and the three zeros are -2, +3, and +1. Well, what you need to remember is that each zero came from a factor. Okay, so we just have to, step 1, recreate the factored polynomial, and then step 2, multiply it out. So let's take a look. We'll just call our polynomial f of x. So if -2 is a 0, it came from the factor x plus 2. If 3 is a 0, it came from the factor x minus 3. And if 1 is a 0, it came from the factor x minus 1. So now we have three binomials that we have to multiply together. You just start by picking two of them and you FOIL. So this is going to give us x squared minus 3x minus 1x makes minus 4x in the middle, and then plus 3. So now I have a trinomial times a binomial, so I just have to do the distributive property twice. If I take the x from the x plus 2 and I multiply it all the way across, I get x cubed minus 4x squared plus 3x. And then if I take the 2 from the binomial and I multiply it all the way across, I'm going to get positive 2x squared, negative 8x, and positive 6. And now I'm just going to combine like terms. So I get x cubed minus 2x squared minus 5x plus 6. This is the polynomial f of x that has the three zeros that were specified.